Yeah. Hello, good morning, everyone, and welcome back to Heat Transfer. So, in the last class, which was on Monday, we had started our discussion on convective heat transfer or convection. However, what we did was we did some recap of some basic concepts of fluid mechanics, which are going to be very important for our discussion on convection. Because convection, as I said, is heat transfer that involves bulk movement of the fluid. Okay. So therefore, since movement of fluid is involved, fluid mechanics form a very, very intimate or relationship with heat transfer. Okay. In other words, the amount of heat that is going to be dissipated, the temperature field, next to a heated surface, uh, these are all going to be dependent or strongly dependent on the flow that is happening around, right? So therefore, the flow and the heat transfer, the flow field and the temperature field are very, very intimately related. Okay. So today what we will do is we will jump into forced convection. Okay. We covered a little bit of what we covered in the uh, recap of fluid mechanics was left, but what I, especially for internal flows, uh, we just covered what is friction factor and thanks to Vatsalya's question. But what we will do is when we come to forced convection for internal flows, we will recap those concepts again. So let us get started today with forced convection, and within forced convection we will start with what is called external flows. Okay, so I hope all of you can see my screen here. When I say forced convection, remember the word forced. What do I mean by that? So this we have discussed before, why we are calling this forced convection. So forced convection is when the fluid is quote unquote forced to flow, right? What do I mean by that? Which means that you need an external agent like a pump, like a fan, like a blower to make this fluid flow. Okay. Otherwise, the fluid will be stationary. Okay. So need an external agency. Example: fan, pump, blower. Okay. Like example, flow through a pipe, right? Primarily by a pump. In your plumbing lines, the reason why the water is coming to your home is because there is a pump that raises the water from wherever the water sump is, typically in the ground floor or wherever it is coming from. It pumps it to some overhead tank, and from there, yeah, from there, it is primarily through gravity that it is coming to the different uh, outlets within your house. But otherwise, if you have to make fluid flow through a pipe, it has to be through a pump. Okay, flow over a turbine blade. right? Why does the flow flow over a turbine blade? Because it is at a higher pressure. Okay. So finally, it's a pressure-driven flow. You have to raise the pressure, whether you do it through a fan, through a pump, through a blower, through a compressor. Okay. We studied shell and tube heat exchanger. So flow over tubes in a heat exchanger. Yeah, we just say that okay, there is an m dot of hot fluid and cold fluid, but how is this m dot coming? Okay, what is the cause? So therefore, the three examples that I said are as follows. So there is flow of fluid through a pipe. Okay, so let us say the fluid is heated. You have studied regular flow through a pipe. Let us say now there is a heater on the walls. Okay, so cold fluid will come in and warm fluid will leave. Okay, similarly, let us say flow over tubes. Okay. The bank of tubes. So if my flow is coming, what will it do? Slight deviation. Something like this. Flow over a turbine blade. Typically it's the other way, but it's okay. Let me draw it in a neutral color. This is typically the cross section of a turbine blade. Typically over a turbine blade, it's a hot fluid that comes in. Okay, and then it will go something like this. Okay. In this case, actually, the heat transfer happens from the hot fluid to the blade. Okay. The other thing I'll say at this point is we'll limit ourselves to single phase. So when the fluid is coming out, there is no change of phase. Let's say from liquid to vapor. Okay, or if it's cooling from vapor to liquid. So there's no boiling, there's no condensation. It's a single phase. Okay. So basically no boiling or condensation. Okay, so this is what we are going to do. So what I'm going to ask you right now is let us consider any hot surface. Okay. I'll consider a hot surface like this. Let us say the gradient along the over which some flow is happening. The liquid, the fluid is at a temperature Tf, and the wall is at a certain temperature Tw, as a result of which there is a rate of heat transfer Q double prime. Okay, I'll call this dimension as X. Okay, now under normal circumstances, this wall temperature will also be a function of X. The fluid temperature will be a function of X. And therefore the heat transfer or heat flux is also going to be a function of X. Okay, so let us write this down. Consider hot surface exposed to a fluid at lower temperature. Okay, so there will be local variations in TW, which is the wall temperature, and TF. So that is TW is a function of X and TF is also a function of X. Okay, so our goal, and this is our goal for forced convection. Why are we doing forced convection? We want to establish a relation between Q double prime X, TWX, and TFX. That's all. You may say, well, Q double prime X is H TW minus TF at X. Absolutely correct. But what is that H? How do I find that H? That is our goal. Okay. Now, sometimes we may not be interested to find out the local variation, but we may be more interested to find out what is the average heat flux, okay, or the average amount of heat transfer. Okay. So, in such cases, sorry. Or what is the average temperature? If my heat flux is known, what is the average temperature? Okay. Sometimes we may not be interested in local variation. Okay. Instead, we may like to relate Q double prime average Q, which is Q over A, total heat transfer over the total surface area, as a function of the average wall temperature and the free stream fluid temperature, or the bulk mean fluid temperature. Okay. So what we do is we define a term which you already know, which is H of X equal to Q double prime X And the average heat transfer coefficient H bar is going to be the total Q wall to fluid divided by area times these average values. Okay. So this is my local heat transfer coefficient, and this is my average heat transfer coefficient. Okay. So in most of the problems that we have studied so far that involve convection and an H value was given to you, it was the average heat transfer coefficient. But heat transfer coefficient can also vary locally. Okay, and we will see that very soon. All right. The other thing is to be noted. Sorry. Note that H or H bar is always positive. That is how it is defined. Okay. The direction of heat flow will be decided whether TW is greater than TF or TW is less than TF. Okay. But H will always be positive. We never say that the heat transfer coefficient is negative. Okay. All right. So this is the very basic definition of what is heat transfer coefficient. And once again, as I said, our goal in terms of convective heat transfer is essentially to find an expression for this H, heat transfer coefficient. Okay, what does it depend on? So on and so forth. Of course, you can, if I ask you right now that what should the heat transfer coefficient be dependent on? Okay. What are the parameters? Okay. What would you say? Let me ask you this question. Let us take the simple case of flow over a flat plate which is heated. Okay. And a cold fluid is flowing over a hot surface. What would the heat transfer coefficient be depending on?
Heat capacity
Heat capacity of what?
of the fluid.
Of the fluid. Okay. So let us write it down. What you're saying is H, let us say Hx is definitely going to be a function of x, and then you're saying Cp of the fluid. Okay. Then
Velocity of the fluid.
velocity of the fluid, U. Okay. What else?
Maybe density.
Okay. Any other thoughts? Of course, when you say density, I'm assuming density of the fluid, right? What else? Okay, you got half 50% right. The other parameters are the viscosity and thermal conductivity. So if you look into this, yeah, we have H. We can club them into mm, primarily three categories. One is X, which is the length scale. Number two is U, which is fluid velocity. And then I can put all of these together, rho, mu, K, and Cp. These are all fluid properties. Okay. So your heat transfer coefficient will be depending on all of these. Okay. So let us do some mental exercise. If I ask you that, again, consider just the flow over a flat plate, the simplest configuration which you are familiar with. And let me ask you that if velocity goes up, if velocity increases, will heat transfer coefficient increase or decrease?
Increase.
Increase. Okay. What about the fluid properties? If density goes up,
Increase.
increase. Okay, why?
It has more atoms per unit volume to store that energy.
Okay. Yeah,
I mean,
that's a
I intuitively thought about air versus water. So yeah.
okay. Right. No, that's true. I mean, even if you don't have this is I'm really happy that you are thinking in these lines. Because right in the first class, I said that we all of us have a lot of knowledge of heat transfer already, just from our regular experiences. Just what you say that, yeah, water cools better than air, we know, and water has higher density. All right. What about specific heat?
I would say it should decrease with specific heat. Oh wait, no increase. Yeah.
Decrease or increase?
Uh, I would say decrease. Yeah.
You would say decrease. Uh, no, actually, it increases because, right, the first logic that you told me that it means for a given unit volume, it can store more energy. When you were describing for density, that's the logic you gave, right? So the same thing, it can store in what is the energy stored is rho Cp, isn't it? So therefore, Cp actually helps. Uh, what about viscosity?
Yeah, viscosity.
Huh?
Yeah, helps. It helps. Increase.
Helps. Well, not necessarily actually. Viscosity.
But
mm,
won't viscosity also depends on velocity?
Viscosity doesn't depend on velocity.
No, not viscosity, but if we consider the contribution of viscosity.
Yes, kind of, yes, because the velocity field will depend on viscosity that way. Yeah, as you will see that viscosity, I mean, it has a, I mean, it's difficult to say. Okay, so we will see that later. Viscosity comes in two parameters. One is called Reynolds number, another is called Prandtl number. We will talk about it, and you will see that there is very dependence. Okay, and what about thermal conductivity?
Helps.
Helps, yes. That is also obvious. Okay. Actually, what happens is you will see viscosity most of the times it hurts, because if you what happens is the inertial forces go down, and therefore the amount of heat that can be dissipated also goes down. All right. So good. I think those are good thought exercises. And now let us try to see if we can put some analysis behind all these. So the first thing that we are going to do is we are going to go back to our good old friends, which are the non-dimensional numbers. We love them. We have already become familiar with several of them, but force convection will be bombarded. But the three most important ones that we are going to talk about, the first one is called the Nusselt number, denoted by Nu and given by HL over Kf. Okay. The second one is called Prandtl number, the same Ludwig Prandtl who was kind of father of boundary layer theory. Okay. Prandtl number is mu Cp by K. And the third one you already know, that is Reynolds number, given by rho u L over mu or UL over nu. Okay, so these are the three terms, and if you look into this, all the variables that we wrote, all the 7 of them, x is the same here as L. Okay, if I wrote an ux, it would have been hx by k, sorry. And what you see is all those 7 independent variables that we wrote, 7, right? X, Cp, U, rho, mu, Kf, 6 and H. Okay, so those 7 variables are all encompassed here in these 3 non-dimensional parameters. Okay, so the first one, let us look into this, and we have to find out that, I mean, just by defining it to be non-dimensional is not good enough. There has to be a physical significance. It's not just about, these are not defined just because their units become 0 or their units cancel out. Okay, so we have to have a physical significance. So let us take them one by one, starting with the Nusselt number. Okay, so firstly, it's the non-dimensional form of the heat transfer coefficient. Clear? Now, what is its physical significance? If you talk about physical significance, I'll cast it in 2 ways. One, I'll say Nu is HL by K, and therefore I can write it as L over Ka divided by 1 over Ha. Okay. So what it means is, if we consider a slab of thickness L and area A, So this is Kf. If we consider a slab of thickness L, slab of fluid, okay? Write that first. Okay. It is a ratio of conduction resistance to convection resistance. Okay. So it's our thermal conduction to our thermal convection. Okay. Now, personally, I don't like this definition. Okay. You will see it in most books actually defined in this way. You will say Nusselt number is actually the ratio of conduction resistance through the fluid over convection resistance. That's very hand waving. And thickness of L, area of A, that doesn't work. And what is area? I mean, it's only true for just a slab. Okay. So it's not a good definition. What I like is the second one, and therefore I'm going to put a star. But again, telling you that you will find the first definition in many sources. It's okay. The second one is much better, and that's what I would like my students to know. Okay. First of all, I would write it. I will write the expression that is del T del y equal to 0 plus divided by TW minus TF over L. Okay. And I will say that this is actually a non-dimensional temperature gradient at the wall. Okay. How did it come? It's simple. We just use H is equals to K del T del Y at y equal to 0 plus divided by TW minus TF. Okay. Because this parameter, remember, is Q double prime. Okay. Therefore, I can write H so I basically replace H by this, and Nusselt number therefore becomes this expression. Now look at this. At the top, what is the numerator? It is the temperature gradient right at the heated wall. If this is my heated wall, this is the temperature gradient of the fluid, definitely. We are all like this, right? So this gradient, this was my TW. right? And this is my TF. No, T infinity, sorry. The TF is varying like this. So let me write TW over here, the wall temperature. So therefore, the amount of heat or heat flux I'm getting is going to be AF del T del Y at y equal to 0 in the fluid direction. So that's why I'm putting it as y0 plus. Okay. So this, friends, now becomes important, and that I'm going to come to that in a bit. Okay. So this temperature, this slope of the temperature that I'm seeing over here, that is del T del Y. Okay. Higher the slope, which means faster is the, not faster, earlier is the temperature drop. Higher the slope, it means that there is higher heat transfer and therefore higher heat transfer coefficient. Right? So that is why if you now look at this, the numerator is the temperature gradient of the fluid at the wall in the fluid side, and the denominator is TW minus TF divided by L. Okay. Now, where F is the bulk fluid temperature at that location. So this is a more scientific definition, and that is what I would like all of you to remember. Acha. Now what I want you to notice is, notice that Nusselt number and Biot number, right, have similar expression, isn't it? Both are HL by K. So what is the difference? If they're both HL by K, then why are they given two different names? What are your thoughts on that?
For Biot number, it is KS.
Right. Note that in Nusselt, the K is of the fluid. That's why I was always writing as KF. Now here onwards, I may not write all the time, but Nusselt number when we are talking about is that of the fluid. Okay. There's a last thing that I would like to point out here, again conceptual. I'm just blowing up what I drew here. Now I say that the temperature, how does it vary? And this we have drawn actually quite a bit. If I plot the temperature, of course, there's a drop in temperature like this. At the surface. Now, before that, what is happening? Let us say it is getting conducted through the fluid. Okay. Before that, if it was getting conducted, the temperature gradient through the solid sorry about that. But before that, this is how the temperature was the temperature gradient look like inside the solid? That was also decreasing, assuming again that the TW is greater than TF, and there's a net heat flow from the solid to the fluid. Okay. So what can I write? See, the heat flux at a certain point that comes to the surface through the solid has to be the same that gets dissipated. So Q double prime X at y equal to 0 minus has to be Q double prime X at y equal to 0 plus. Right? Therefore, this Q double prime. So which implies, or that is equal to, not implies right away. Therefore, this equal to what is y minus? That is conduction through the solid. So minus Ks del T del Y at y equal to 0 minus, and that is also equal to minus Kf del Tf del Y equal to 0 plus. Okay. The temperature below y equal to 0, in the negative direction below y equal to 0, is the temperature of the solid, and above is that of the fluid. So that's why I've written Ts and Tf. Okay. So keep this in mind. Many a times, probably somebody may ask you that the slope of the temperature and inside the solid at the wall is so much. So that will help you to find out what is the slope of the temperature at the wall for the fluid, and from there calculate what is heat transfer coefficient. Okay. So keep this in mind, that if I say that in convection the heat flux is K del T del Y at the surface, it means that it's K del T del Y both in the solid and the fluid. Just as long as you know, if you're using the thermal conductivity of the solid, it is the temperature of it is inside the solid. Okay. So therefore, for Ks greater than Kf, which is many a times the case because air is one of the, especially for air is one of the worst conductors we know. For Ks or Kf, it therefore follows that del Ts del Y at y equal to 0 minus would be smaller than del Tf del Y at y equal to 0 plus, which means therefore the gradient of the temperature in the fluid side will be larger. In order to balance this, in order to have k dt dy balance out. Yeah. Any questions, friends? So this, yes, please.
So like I was thinking about that Biot number counterpart. Does that mean that for a sufficiently thin flow we can like extend the lump system concept?
Sufficiently thin flow. What do you mean by thin flow?
By thin I mean like the L value, thin sheet flow.
No. L actually, this L is not very. It's not a. It's used. It's an arbitrary assumption. This L many a times is the length of the. So this is another problem. It's not this L, as we will see later, is the length of the plate. It's not the thickness of the. It's not the thickness of the fluid. Okay, thickness of the fluid we will see it's the boundary layer thickness, thermal boundary layer thickness. So therefore, again, this is not a good definition. This is, but even the second one is not a good definition. but it is sort of a it's a non-dimensional temperature gradient, and for non-dimensionalization we have used TW minus TF over L, which is not a very good assumption, because TW and TF, right, TW and TF is happening in the y direction. L is the length in the x direction for a flat plate. For a flow over a cylinder or a sphere, again TW minus TF occurs over a small layer normal to the surface of the cylinder or sphere. Whereas the length scale we used L, instead of L we use the diameter of the cylinder or sphere in those cases. Okay, so it's not a good definition, and the first thing is, no, you cannot extend bio. First of all, extending lumped capacitance to convection doesn't make sense, because they are completely unrelated, because lumped capacitance is for finding out the temperature inside the solid, where it's purely conduction, okay, and convection at the boundary. So even anywhere else, when the heat transfer coefficient is very low, it is possible for lumped capacitance to be valid again, provided Biot number is less than 0.1. Okay, that doesn't have any dependence on, on the dimensions or anything. Okay, all right. So we spent a little bit of time on Nusselt number, but that's okay, because that is the central concept. Okay, next, I'll go fast now. Prandtl number is the second one. What is Prandtl number? It's a fluid property, number one. Completely fluid property, has no dependence either on geometry or on the flow. Okay. The definition here is, it's a measure of momentum diffusivity over thermal diffusivity. Look, we defined it as Prandtl number is mu Cp by K. Okay, mu Cp by K. But what I can write is, I can just reframe this and write as mu over rho, similarly Kf over rho Cp. What is mu over rho? Nu. And what is K over rho Cp? Alpha. Okay. The one you see nu, you have learned it as kinematic viscosity. It is also called momentum diffusivity. Okay. And alpha, we have defined it and we have learned it as thermal diffusivity. Okay. So what is it actually signifying? Okay, it is what it is signifying is that it's the measure of the ease. It's the measure of the ease of transfer of momentum or shear forces to the transfer of thermal energy through the fluid. Okay. Look, higher is the viscosity. It means that the effect of the shear forces at the solid wall is going to be felt over a larger distance, right? Similarly, higher is the thermal diffusivity. It means that the effect of this heated plate, which is suddenly introduced inside the fluid, that is going to be felt over a larger volume of the fluid flowing over the plate. Okay. So in other words, the thermal disturbance is going to propagate or penetrate for a larger depth into the fluid. as you move up from the heated surface if the thermal diffusivity is higher. And similarly, the effect of the viscous forces at the wall, which results in the no-slip boundary condition and gives rise to shear forces, that effect is going to be felt over a larger distance away from the heated wall, away from the wall, if the viscosity is high, right? So therefore, that's how you have to physically visualize. It's a measure of the ease the transfer of viscous or shear forces to compared to. Okay, I have not used ratio. So compared to the transfer of thermal energy through the fluid. Okay. So as you can see, a few things. That viscous fluids have high Prandtl number. Okay. High conductivity fluids like mercury, etc., have low Prandtl number. Okay. So I can give you some values here. For gases, Prandtl number is of the order of 1. Okay. And why? Because mu and K are both low. To give you an example, Prandtl number of air at room temperature is around 0.7. You can remember this. I would request you to remember Prandtl number equals to 0.7 and therefore slightly less than 1. This is for gases. For oil, because oil is very viscous, right? So Prandtl number is around 100. Why? Because of high viscosity. Okay. Liquid metal. Prandtl number is like 0.01 or so because very high thermal conductivity. This is like mercury, liquid sodium, potassium, etc., etc. Okay. So Prandtl number of air is 0.7 and Prandtl number of water is 7 at room temperature. Okay. So air doesn't change much in the typically in the range that we work in, but Prandtl number of water changes quite a bit. At room temperature like 25 degrees or so, it is 7. If you go to some 70, 80 degrees, it becomes like 5, 4.5, and so on. And the reason is, as you heat up, as the temperature goes up, the viscosity goes down. Okay. Thermal conductivity also goes up a little bit, but primarily because viscosity reduces, the Prandtl number goes down for water as you heat it up. Okay. But this is very handy to remember. Prandtl number of air is 0.7 and Prandtl number of water is 7. Easy to remember at room temperature. Okay. So I would request you guys to remember this because it helps. It helps in multiple ways. We will see that. The last one before we break is Reynolds number. Okay, and this you already know. I have nothing else to cover here. Reynolds number is a measure of inertial forces over viscous forces, and it's typically given by U times L for nu or mu UL, rho UL over mu. Clear? Okay, so it's 8:57. Let's take a break now for 5 minutes, and I'll come back. Okay, so during the break, please go through the notes just to make sure that you have understood everything. After we come back, we'll go into governing equations. We already know about continuity and momentum from fluid mechanics, and we are going to talk about another one called energy equation. Energy equation, I'm not going to solve it again because it's a, it's more of a mathematical exercise. So what I will do is I will probably just write it up and give it. I'll give you the final form here, and the derivation I'm just going to derive it, scan it, and upload. Okay, because yeah, no point spending time over that. And okay, so let us meet after this break. Thank you.